All right, hello, hello. So today with Phys, it's going to be pretty light. There's not going to be too terribly much, that's what I say now, but we'll see what we do. So it's going to start off with valves of the heart. How do those work? When are they open? When are they closed? How can we visualize that? And if you can actually visualize it, it makes it a lot easier to hold on to it as you go through your life, but your course load and all that sort of thing. And when it comes back up again, you are able to hold on to the concept that lets you reason out, oh, that's going to be a systolic murmur because of da 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 da. Or I heard that and it was a systolic murmur, therefore it'll be one of these things. So playing with the valves first, then we'll go into looking at how we can chart the pressures and volumes of the heart. So ventricle when it's relaxed, ventricle when it's squeezing, looking at the pressure going on, as well as in the aorta, pressure in the aorta. Those two are particularly important. And then also looking at the volume of blood in the ventricle, looking at the volume of blood that's moved out of the ventricle into the aorta. Go into stuff like that. There's lots of ways to chart that, and that information gives us a lot of info about how the heart is doing. So we will go ahead and start with the valves. All right. Here's our heart. It's anatomically correct and perfect. Everything in the world is rosy. All right. The valve that moves from the left atria. Everything in the world is rosy. All right. The valve that moves from the left atria down to the left ventricle is a one-way valve that opens down into the ventricle. This will happen when the pressure in the atria is higher than the pressure in the ventricle. If the pressure in the ventricle is higher, so the ventricle squeezing, this can't go further up, but it can open down. And if you try to push it back up, then you have blood pushing here and it'll slam it closed. One-way door. Okay? If you break the chordae tendonae, or what they call, they're little strings of muscle that keep it from going back further. If those snap, then you have a problem, and it's called regurg or regurgitation. And that would be systolic regurg. And then it would give you this kind of burbly sound when you're listening. But if everything's working normally, one-way valve, mitral valve when it's on the left side of the heart. Okay? So, then over here, let's go ahead and draw the aorta in purple. Crossing over the top. There's our aorta, and if that's the aorta, then it makes sense that the valve would be called the aortic valve. The aortic valve is also a one-way valve, and it opens like this. When the ventricles squeeze down below and they pressurize all the blood, it gets pressured enough that it can pop that open. All the blood squirts out through the valve, and then eventually it's kind of like, if imagine a water bottle, you squeeze it really hard. At the beginning, lots of water comes out, right? Because it's in there. Eventually, the water is going to go from spraying out to just a little out to no more going out. And when you don't have anything spraying to hold that open anymore, all the rest of the blood in the body has some pressure, and it will be greater than the spraying pressure after it's run out of blood to spray out, and that'll come and slam the doors closed. Okay? Squeeze the ventricles, pops it open, and run out of stuff, slams closed. This can also break and go in reverse in a pathological condition, and that would be aortic regurg. And that would be a diastolic murmur, which we'll get into. So those are the two valves, mitral and aortic. All right. Throw extra letters in wherever I go because I'm just that kind of philanthropic person. All right. So now let's go through the phases of the heart, the way blood moves through it, and do the valves with those at the same time. So, actually, first let's do some definitions. Systole. Do you know what that is? Systole is when, and so systole means phase of squeezing, so contraction. And medically, we almost always, if we just say systole, we mean ventricular systole. We almost don't even care about the atria. And so if we specifically say atrial systole, okay, fine. We're talking about the atria squeezing. But if we just say systole, we're talking about the ventricles squeezing. Hello, come on in. So I'm going over the valves of the heart and stuff like that.
I have one for physiology.
Mm-hmm.
Okay.
Okay. Good deal. We were just going into blood flow, so let's go ahead. You're here live, so I mean, what's your question? We're going to take a pause and take a question, and then we'll get back into it as we do.
Are there people watching?
Most of them are live. There's one right now. But
so it was on this worksheet, and you don't have to give me the answer, but if we could go over how does end systolic volume change when beta adrenergic receptors are activated at the surface of cardiac mount? Like, I don't even understand that.
okay.
And then basically that whole question, like, I didn't even know how to start it. So I don't really understand what.
Good deal. All right. Okay, so the question is, how does end systolic volume get affected when beta adrenergic receptors of the heart are stimulated? So if you have beta receptors turned on a lot, what does that do to how much blood you have left at the end of systole? And that actually plays into what we're kind of going into. So we'll go through this, and then we'll answer this question at the end of that, and then that'll actually help make it make a lot more sense. So here we go. So in order to answer that, so systole is when it's contraction. We're going to go over definitions first. Systole is usually referring to ventricles contracting. Systole just means contraction, though. So if we say atrial systole, then it's going to be the atria. If we just say systole, though, medically we're defaulting to the ventricles. Okay. So diastole then is just whenever we're relaxing. So if the ventricles are going to be, let's go into blood flow. We have iso, meaning same, and then volumetric, isovolumetric. I'm going to start with filling. So this is going to be during diastole, and we're talking about when, let's go ahead and draw this properly. So we've just finished squeezing blood out of the ventricle into the aorta, and then we ran out of blood to squeeze out, more or less, and so then the aortic valve slammed closed, and we'll talk more about that in a little bit. And the mitral valve is still closed because the ventricle is still squeezing some, and then it relaxes a little more, and as it relaxes out, it started at a pressure, let's just make up a pressure, 100, goes down to a pressure of 50. This pressure of 100 or pressure of 50 is still pushing on this one-way mitral valve, and that holds it closed. And so you'll notice both valves are closed, and as it gets down in pressure, finally this mitral valve, there's a bunch of blood resting on top of it, will have enough pressure on the top side that it will outweigh the pressure in the ventricle, and it will push the mitral valve back open. And then we'll begin filling. Before that, the volume of blood that was in the ventricle wasn't changing because both valves were closed. And that's what we call isovolumetric relaxation, and that happens during diastole. So we relaxed, but both of the valves were closed, so nothing was coming in. As soon as the pressure in the ventricle gets low enough that the mitral valve can open, we have gravity bringing in a bunch of blood from the atria, and that'll be called rapid filling. And all this blood gets dumped by gravity, and eventually there's only a little bit of blood kind of trickling through, and then that's going to be called slow or reduced or something like that, filling. And then there's a few dregs left in the side, wring it out by actually contracting the atria, and that will be atrial contraction or atrial systole. So I'm going to put contraction though. And that would make so that we have more blood coming down here into the ventricle, which is now, so we got some blood in rapid, we got some more in slow, and then we got some more in atrial. And actually, most of it comes in rapid. And then in slow filling, you get a little bit more. And then at resting heart rate, atrial systole does next to nothing. There's actually only a few dregs left that are put in. Okay, so for each of these phases, these ones are actually filling, whereas the isovolumetric, both of the doors were closed, no blood's moving. All right, so now we have blood in here. Now, as the ventricle moves into systole, contraction, then we're going to build up pressure. And that pressure is going to be pushing against the aortic valve now and trying to close it. And as soon as it starts contracting, it's also going to push against the mitral valve. And the mitral valve doesn't have any blood on top of it anymore. The atria aren't squeezing anymore, so there's really nothing trying to hold that door open anymore. So it will close really easily. So as soon as the ventricles start to contract, this slams closed. And we can actually hear that.
And is that called atrial diastole?
Yes.
Oh, there is.
So that would be atrial diastole. If we just say diastole, we're talking about the ventricles. But if you, so this, let's go ahead and right over here.
Is that the lub or the dome?
That would be the lub, because it's at the beginning of the systole.
Right.
And so your first sound is the mitral valve slamming closed. And we are in ventricular systole, or systole of the heart, systole. And we've just barely started isovolumetric contraction. And I'll just put a C for contraction. So we start squeezing, and we've slammed the mitral valve closed, but we can't. So in the body, all the blood that's left in the systemic circulation, it's still there. If I like to imagine if there was a trapdoor in the ceiling and there was a bunch of water on top of it, and we were trying to push that trapdoor open, the more water that was on top of it, the harder we'd have to push. That's exactly what's going on here. And if that water was in a small space and it was like pressurized, then it would be even harder to open it. And that's what's going on here. So you have a bunch of blood on top of this, and so the ventricle starts squeezing, and that pressurizes everything inside of it, but it's not enough to open this because we also have pressure pushing back down. So we push harder. Still doesn't open. We push harder, and finally we will have enough to actually pop the valve open, and we will have all this pressurized stuff squirt out rapidly. So when it wasn't moving, it's isovolumetric, no movement, no volume change, and then squirt, or rapid ejection. And then just like a water bottle that you're squeezing and you have stuff coming out of, it will slow down after the initial burst. And then that would be reduced ejection or slowed ejection. And then we would run out of pressure down here, and all the blood would come storming back down the aorta here and slam the doors closed by pushing from above. And we hear that closure. So notice both of the things we hear are valves being slammed closed. This one would be the dub sound. All right, so with this, and I do remember your question, we're getting there as we build to it. With this, if you can remember which way that the valves are one way, and you can remember what squeezing the ventricles would do, then that will help you to be able to reason out, oh, if I hear something after the lub, there's only two things that could be going on. Like if I hear a weird sound, it could be that this valve is broken and so we got leakage going backwards, or it could be that this valve is stuck and it's not opening all the way and so it goes shh as it's rubbing against the valve. And so this one would be called stenosis, this one would be called regurg, aortic stenosis, mitral regurg, and just by seeing that when we're in systole, those are the two ways that the valves could break. Those are the two issues we could be hearing. And that will come up later.
There's also pulmonary stenosis.
Yes, on the right side of the heart, same idea. We would have the pulmonary artery that we would be talking about then. Pulmonary stenosis, correct, also during systole.
It's such a small volume that it's not really focused on it.
The left side of the heart is just generally one where you see more issues, and so it's a good example. But you do want to know the right side as well, and where you're listening with your stethoscope will help you determine whether, okay, this would be a left-sided issue, this would be a right-sided issue if we hear it loudest right here.
Does the lub actually both, the tricuspid and mitral?
Yes.
Okay.
Yep.
Okay.
And then the dub would be the pulmonary and aortic going at the same time. Good question. All right. So, honestly, maybe this is something that you guys are all good with. If not, something that really helped me in getting together is basically what I already said. Try to visualize a ventricle or a water balloon or whatever that has two doors that are one way, and just squeeze it, watch what happens, and try to watch it as a movie that you make for yourself. I know it sounds really simple, but it really helped me have it so that when I forgot the memorized stuff, I could reason out all of the issues.
Is S3 and S4, are those normal sounds or are those only abnormal?
So S3 and S4, those are normal. There are abnormal versions of them, but S3, you know what, I haven't looked at those in a while, so forget anything I said about them. I don't remember for sure. I think that they're normal, but I don't want to swear to it. I haven't looked at them in a while. Good question. Bad answer. So.
Well, it's too late now. We already had our cooker.
Yeah. All right. So let's do a couple graphs now, and that will get to the question that you had. So if we have a graph like this, and we have pressure on the y-axis, and we have volume on the x-axis. We can have volume of the heart, let's say that this is roughly 50, and then this goes up to, we'll just say 150. As we have the heart filling, it would look roughly like that. You're just letting, as we have the ventricle filling, it's just dumping down into there. There's not too much pressure going on. There's no squeezing really, unless a little bit of the atria squeezing it down, but mostly there's not pressure going on. Then, once we have systole begin, we start squeezing, but none of the blood goes anywhere, and so we don't go anywhere side to side. We just go straight up, squeeze, build up pressure, but no blood is going anywhere because the mitral valve slams closed, and we don't have enough blood to pressure to overcome the pressure of the body, the systemic circulation. Until finally, we overcome it, and we squirt blood out. We squirt it out first really energetically, and then it gets less energetic towards the end, just like that water bottle that runs out of stuff to squirt out. And then eventually we don't have enough pressure to keep this valve open anymore. It slams closed, and then we relax. But even while we're relaxing, we have a little bit of pressure left still. It hasn't relaxed all the way, and so the mitral valve stays closed because it's very easy to keep the mitral valve closed. We get all the way back down to the beginning. and the cycle starts again. So when you're looking at these, you can look at the bottom. This is filling. The side, squeezing, but no movement of blood. And then at the top, ejecting or squirting it out. So fill, squeeze, spray, relax. Fill, squeeze, spray, relax. Now, to your question, what would happen if we stimulated beta adrenergic receptors of the heart? Beta adrenergic receptors, the word sympathetic, excellent. And so we have the sympathetic system activated when we are fight or flight. Fight. And so we want to have more ability to basically exercise, do hard work. And so we're going to increase the strength of the heartbeat. So beta adrenergic, the adrenergic part tells you it's sympathetic, means that we want to squeeze harder. And so if we squeeze harder, then we're going to be able to eject even more. I'm going to use a different color here. And we actually have so much squeezing going on that we manage to get rid of even more of the blood, and there's less left over. And then we relax down to here and go through the whole thing again and go up, squeeze, squirt out extra. And so we would end up, normally we have, after we squeeze, we actually have some blood left over in a normal squeeze. As you see, we don't ever get down to zero volume. And so this is what we call end systolic volume. And our end systolic volume, if we squeeze harder, would it be higher or lower? How much we have left over?
Lower volume.
Lower.
More ejected.
Because we squeezed it even harder, more of it ejected, exactly. So we can see that going on. Let's do a couple other terms. So the answer to the question was?
More forceful contraction ejects more volume.
More forceful contraction because of the beta receptors. More volume gets ejected, less stays behind. Exactly. All right. Let's do a couple terms since we did end systolic volume. End systolic volume is after systole. Go ahead and get rid of this. End diastolic volume is after all the blood has been poured down in there, right? So at the end of diastole, we've done all of the filling phases. And so the blood is going to be pretty much the whole amount. End diastolic volume. You could almost say end filling volume, end of all the filling stuff volume. It's our max volume. Another term.
Wait, can you go over that again, the end diastolic?
Sure. Let me go ahead and get rid of the mess up here. All right. So when we're in systole just ended, and so this just opened, the mitral valve just opened, and all the blood that has been in the atria, now gravity pours it down. And so it fills, and it fills, and it fills, and it fills, and then we squeeze out the last bits, and it fills, and then atria have squeezed, that's the last part of diastole. And so in diastolic volume, after all the blood that's going to come into the ventricle has done so.
Yes.
Okay. So something that is almost synonymous with end diastolic volume is the term preload. It's just how much blood is in there before we start squeezing. This brings us to the other word that sounds like it should be the opposite of preload, and it's not. Preload, just to say it another way, preload equals the volume of blood in the ventricles before systole. Afterload. You would think afterload would be the volume of blood in the ventricles after systole. But it isn't volume, it isn't the ventricles, and it isn't even really related to systole. So afterload is a completely different thing, but they sound so similar that I just want to point out how much they're not. Because myself, someone from an upper cohort, and some people I've talked to in lower cohort, everybody has gotten afterload mixed up, so I want to make a point of it because it's just that ridiculous. Afterload, nothing to do with preload. Afterload is actually a pressure. Remember how we talked about right here how you can have some fluid in the rest of the circulation, some blood in the rest of the circulation that rests on that trap door and makes it hard to open it? That pressure, you can have high blood pressure in the systemics, and that makes it even harder to open. That pressure right there, when we measure that, we call that afterload. So it's pressure of the fluid in the aorta. Or in other words, the pressure holding the aortic valve closed. Pressure.
I think the textbook said that preload also was a pressure, the amount of force on the muscle just before it contracts, which is the volume is making that force.
Okay, I could see that. So preload. All right, so volume creates the pressure. Thank you for the correction. Pressure inside the ventricles, pressure inside the aorta. Volume creates the pressure with the preload. Okay, good deal. So, with that, stroke volume. We can see that in diastolic and in systolic, they have this difference. And that difference is basically how much got squirted out. We call that squirted out amount stroke volume. So how much got lost? Stroke volume would just be how much was moved. And then something very similar to stroke volume is ejection fraction.
Yeah.
And ejection fraction is very similar to stroke volume, except now we're expressing it in a percentage. And so it's what percentage of the blood left. And so we do that by stroke volume over end diastolic volume times 100 equals whatever. And that equals percentage of the blood that left. So amount that left over total amount, multiply by 100 to make it a percent. And then that is our ejection fraction, which is measuring pretty much the same thing as stroke volume, but expressing it in a different way. Okay, the purpose for these is because stroke volume, people don't all have hearts that move the same amount. Like if you were to measure 100 milliliters being moved, people, I think it's usually 70, but people who exercise a lot or are naturally larger and have a larger heart, their stroke volume could be, their normal stroke volume would be higher. Their ejection fraction, though, should stay the same relative to someone else who exercised and so on and so forth as much as them, give or take. And so Ejection fraction is kind of a measurement of how healthy your heart is, how well it's moving for its own size. It's controlled for size and that sort of a thing. Whereas stroke volume, 70 might be good for one person, but not good for someone else. So, pressure volume charts. Anything else on those?
Yeah, so one of the, also on that same worksheet, 8 different parts and phases of the cardiac cycle, and I only counted 7. It looks like you only have 7 too, like isovolumetric, rapid filling, slow filling. So I added the 8th one as atrial diastole and ventricular systole, but is that considered one of the phases?
I think they might be counting atrial contraction. So I know what worksheet you're looking at there and what he has in his slides. He has atrial systole listed in both diastole of the heart and systole of the heart.
Yes.
And I think that's why he lists 8, is because that step is kind of on the cusp. It's the beginning of he marked it as the beginning of systole when it isn't really, because he shows it at the beginning of systole just to give the example of this just happened, and then we move into the rest of it, and I think he just saw that wrong. So I think there's only 7.
Atrial contraction and atrial systole are the same. Yes.
Yeah, they are.
So there's not, I shouldn't write atrial diastole or ventricular systole.
Yeah. It's not wrong though, so you can leave it there if you like. Because when the ventricles are squeezing, the atria are relaxing. Let's do another pressure volume chart here. If we had greater preload, greater preload, let's go with that. I'll use red for that. If we had greater preload, then that means we're probably exercising. And that makes so that our atria are receiving more blood, and so when they squeeze, instead of just doing dregs, they actually are squeezing an amount that's real. And so we get extra volume, and actually there's some pressure there too. And then with that extra volume, we get more squeezing, and then we eject all the way back. And so we shift, we broaden it, which means that we're filling more and squeezing more, both. And so this red one would be increased preload. We just shoved more blood into there, and that caused more pressure and more volume, and therefore we are able to squeeze out more because there's more in there to start with. Why is it easier to squeeze out more when we put more in? That relates to something that we should touch on, Starling's law. So if you take a water balloon and you put just a little bit of water into it, you don't need to, like one of those small water balloons that's really hard to blow up. If you just put a little bit of water into it, it's not going to come back out, it'll just sit there. But if you put maybe an ounce of water in and then let go of it, it'll shoot some of it back. So if you put 2 ounces in, it'll squeeze back even more, because then it's stretched out even more and it wants to come back even more. That's Starling's law. The other part of Starling's law is if you put in a bunch, eventually the balloon just kind of stretches and gives up. And then after something like, let's just say 8 ounces or something like that, it's not going to shoot, it's not going to continue to increase how pressure it'll shoot out with. So Starling's law, we could look at a graph like this. As we increase both the pressure, as we increase the volume, we also increase the pressure to a point, and then we start to see it taper off. So we're increasing volume the whole time. For the first part of it, that also increases the amount of pressure that will be expressed. So Starling's law is just measuring how does more volume affect the pressure of the contents, or the pressure of the ejection. Volume related to pressure. By adding more volume, but not crazy amounts, so we're in this half. By adding more volume, that makes squeezing happen even more. So we got more pressure in squeezing out. So just like that water balloon, if we started with 2 ounces in it, that would give us a recoil value of so much.
The amount of volume that we're putting in is what we're injecting.
The amount of volume we're putting in is affecting how hard we squeeze. And that also affects how much we'll squeeze out. So if we put in 2 ounces into a water balloon, it'll squeeze X amount. If we put 3 ounces in, then that'll make it squeeze even harder because it wants to get back to its normal shape even more. And so as long as we don't overload it and go over here where it's like, now we're breaking stuff, then the recoil will continue to get stronger. So the more you fill it, the more it wants to get back to normal. And that's Starling's curve. Did that make sense?
And what's the blue dotted or the purple dotted one?
The purple dotted one, this is increased contractility. This one is you fill it and so it recoils back. That's preload. This one is you actually are saying squeeze harder with like just not because of stretchiness, but because you're actually commanding it.
Because of the beta adrenergic.
Right. This is contract harder because we're telling you to try harder, not just react through recoil. This one's kind of recoil. This one is actually work, contract harder. Then there's one other one that he brings up, and the contract harder, this is going to be like exercise. Oh, excuse me, I don't want to say which one's exercise because I would have to double check. To me, it's like both of them make sense for exercise. You're contracting harder and whatever. So you can look at your thing for which one he calls exercise. But there is also afterload. And afterload makes it really, really hard to open what?
Are you asking about the valve? Oh yeah, okay. The aortic valve.
Right. And so it's really hard to open the aortic valve, which is right there. Then we need more pressure. Let's grab a third color. All right. Me too. So we have to spend more time squeezing. And by the time we finally get it open, we only have a little bit of time to shoot out blood. And this whole thing would actually be shifted to the right, but I'm going to keep it here just for the idea because it makes it easier since we've already have it drawn. And then it would come down and it would be roughly right here. And then it would actually go out over here and go up. And it only squeezes out. It spends half of its time, let's say, getting its pressure up.
Higher afterload is less volume.
Higher afterload means we have less time and therefore eject less volume. Yes. And then since we ejected less, we have more that stays left over. This is our end diastolic volume.
Yes.
And then we shove a whole bunch of blood on top of that. And so now we're like clear over here where we have this kind of a thing going on where it's actually shifted all the way over. Right? It's not right here, it's actually over here. And that's because we keep cramming more blood in, and so the volume is always high. And this leads to backing up because the atria can't get rid of all the blood because the ventricle doesn't have room, so the atria has some left over. And so when the lungs try and dump more into the atria doesn't have room because it's got too much. And so this guy pushes some back here, this guy pushes some back into the lungs push it back into the right side of the heart pushes it back out into the body, and that's what we call left-sided heart failure for one thing, and congestive heart failure, and then right-sided heart failure, and it just backs up all through the body.
Why is it called congestive heart failure?
Congestive heart failure is the whole thing going on, and it's because it's congested, like congested traffic. Too many cars, can't move. Too much blood, can't move.
Why does that cause hard to breathe?
Good question. Why does it make it hard to breathe?
Is the heart is bigger?
That's a good thought. It's actually because if it backs up, if the blood backs up from the ventricle to the atria to the lungs, we literally have more fluid in the lungs. And the lungs are made to be able to exchange gases, and some side effects of that are that it's got some capillaries that are willing to leak a little, and we get fluid on the lungs. And then lungs full of fluid sounds an awful lot like drowning. So it's on the other side of the tissue, but it makes it very hard to breathe and have gas exchange, and you don't get very much across because then it has to cross a lot more fluid before it reaches the capillaries. So you have the airspace. It's supposed to be capillaries close, but if capillaries are farther away through all the fluid, or if the fluid overflows into the alveoli. So yeah, fun, not fun. Congestive heart failure. All right. Your heart will keep getting better at squeezing it out, and it's like, I can do this, until eventually it goes onto the other side of the Starling curve. And then it gets worse and worse and worse because, yes, more and more keeps staying in there, which means it's better at first, and then eventually you get so much back up that it actually can't keep up, and it makes it weaker and weaker recoil. And so at that point, we call it left-sided heart failure, which leads to congestive heart failure, which leads to right-sided heart failure, and then everything failure. So if someone has a damaged heart and they can only get up to there with their recoil for whatever reason, we can give them something. Do you happen to know what that drug might be called, or the plant?
I do.
Starts with a D. Digitalis. Or foxglove. And that'll go ahead and pump it up. And in fight or flight, we naturally will use epinephrine to pump it up the same way. Okay, so good deal. Is there anything else that you'd like to go over? All right, I think that's what I had prepared. See if there's anything else that comes to mind. I'll go ahead and ask a few questions. Don't need to answer out loud. This is just so that you can do some review in your mind, and so can you guys. So, first off, what is stroke volume? Stroke volume is the actual amount of blood that is moved out of the ventricles when they squeeze. Awesome. All right. Which corner of the pressure volume chart represents the opening of the aortic valve? I'll say that again. Which corner of the pressure volume chart represents the opening of the aortic valve? Give you a few seconds. Corner 3, so the top right corner. Closing of the aortic valve then is corner 4. All right. So you can always remember the pressure volume chart. The top ones are aortic, open, close. The bottom ones then are mitral, open, close.
And also tricuspid, but we're not focused on it because it's not the left ventricle.
Exactly. Mitral and tricuspid share the same kind of thing going on, which actually, really good question comes out of that. And aortic and pulmonary share the same kind of thing. Here's a question. Which side of the heart moves more blood, the left or the right?
Left.
It's a trick question. They actually move the same amount. I'm a horrible, evil person. All right. Good deal. Filling, squeezing, ejecting, and I'm going to draw one more chart. You guys have a chart that looks kind of like this, something remotely like that, and then it has a dot right here, a dot right here, a dot right here, and a dot right here. This is just showing the pressure in the ventricles. This is the mitral valve closing because the pressure starts to build up. And this is the chart that is really helpful if you can visualize if pressure starts to build up, which slams closed. Mitral closes really fast because there's no fluid on the top anymore, trying to hold it open. And then once the mitral slams closed, we have aortic open, and then aortic close. And then we go back to mitral open. And then we have all the filling phases that we talked about. And so these ones were all the ejection phases in the high pressure stuff. So all this would be systole. All of this would be diastole. All right. Hopefully this helped. And I'll catch you guys next time.
Thanks for dissecting that question.